Right, yeah. So after the heavy morning session, now something light, so light flavors. And this is based on work I've been doing with Sergei Alyoshin, collaborators over the past years. And then more recently, this is why New Physics, there were a couple of BSM people coming to me asking about parton distributions for searches. So we looked into this a little bit. So this is Yuri Fioski, Francesco Giulia, Hautmann, and Stefano Moretti. So we looked into this, and this is the subject I'd like to talk to you about. And then there was also recent work together with Sergei Alyoshin, Sergei Kulagin, and Maria Vittoria Gazzelli, where we were looking at sequence data and what it tells us about light flavor parton distribution. So somehow these two works connect. And then there is also ongoing work with Sasha Genayev and Andriy Antaychuk and others, where we also look at forward-backward asymmetry for Drell-Yan production and how that can be further used as a tool also for experimentalists doing searches. So the setup is the basic one. So we use QCD factorization, where we are interested in the hadronic cross-section for some process of interest. In this case, we'd be looking at primarily at Z boson production. And then there is the hard scattering cross-section in the middle here, which most of us are concerned with. We try to compute it to higher and higher orders in perturbation theory. And now the topic of this talk is basically, we'll be looking at the non-perturbative parts left and right. So what's our knowledge on the parton distributions, especially in the light flavor content of the partons in the proton here that give rise to the parton luminosity. And just to bring you all on one page, the parton kinematics at the LHC can be described in this plot here, where on the horizontal axis we have the parton momentum fractions x, and on the vertical axis we have the hard scale q. So this is a log scale here, starting both log scales, so starting going down to x values of 10 to the minus 7 and all the way up to 1. And then on the horizontal axis we are starting here somewhere at whatever 1 GeV, 10 GeV. And then the parton kinematics, which has been covered before by deep inelastic scattering experiments like HERA or other deep inelastic fixed target experiments where you have an electron probing a proton. It's given here purple wedge here. And then the HERA, the LHC kinematics, this is this blue triangle here. The blue triangle is for 7 TeV, and then the gray triangle is for 13 TeV, so it extends a little bit. And those dashed tilted lines, they denote the rapidity in your detector. So basically it means that if you're looking somewhere between rapidity -2 and 2 in your detector, and you're looking for particle production of a particle of 1 TeV or even higher, then you're squeezed to this large X part of parton kinematics. So you're sitting here at high scales, and you're sitting here at X values of 10 to the minus 1 to 1. So this is really the corner of phase space that we're looking at when we're doing new physics searches. And then the question is, how well can we understand this? And we have been doing some years ago, we have been doing a global fit of parton distribution functions, this ABMP16 analysis, and this used a lot of data sets, basically covering this whole plane from deep inelastic scattering experiments, but also LHC data in order to extract PDFs to what we would say good precision. Just to point it out to you, so the bulk of the data in any global PDF fit is still coming from HERA data, or from inclusive DIS data, I should say. You see here, this is of the order of 2,000 data points. And then we keep, with runs of the LHC, we keep adding LHC data. So in 2017, we had here of the order of 170 data points for W+, W-, and Z boson production as function of rapidity. and we keep updating this, but just to give you a gist of what data is determining those PDF fits. And then we have our base data set. We know this data is compatible. We then check compatibility of a new data set, like in the case of sequest, which I'll talk about later, and then look at the constraints, and then we run the fit again. So this is the type of iterative cycle that basically any global PDF fit does. And specifically the Drell-Yan data in the ABMP16 analysis, the set is 172 data points. Since this has been measured differential in rapidity, it gives us access to the partonic X values especially of the light flavor partons. It has sensitivity down to X values of 10 to the -4. And you can understand this by just looking at the leading order kinematics. When you have W plus boson production, this is, for example, a U quark, which you probe at X2, multiplied by an anti-D probed at X1. The W minus is the other combination. You flip up and down, and the Z boson is basically the sum of the charge-weighted products of U times U bar, D times D bar at these different X values. And then if you have it in bins of rapidity, you can basically really access the individual X values there. And this is to be compared with DAS cross sections, which typically always give you the sum of the valence U and D. So there, the C quark are less accessible only indirectly via the evolution. And then when you do these PDF fits, of course, you have to think, okay, what are you parameterizing? So you have to choose a functional form. And typically most of the global fitters use some functional form which parameterizes then quark and gluon PDFs as a function of X. And I think what all of them have in common, there is some normalization prefactor, and then there is some small x part. So this is x to some power. Then there is a large x part, 1 minus x to some other power. And then there is some ansatz for a polynomial or whatever function that you have for joining the two ends of the kinematic spectrum. And if we're interested in new physics searches, then I highlighted here this large X behavior. So just keep in mind, large X PDFs are parameterized as 1 minus X to some power. And typically in our ABMP fit, those powers range between 3 and 8. So for example, for the U valence, this is 3.443 plus minus 0.064. So also to give you an idea on the accuracy that you reach in fitting this exponent when we use all this data. Then the C quark exponent is a bit larger. It is close to 8. It's a bit less precise. So these are typically the numbers we are talking here. Right, and then there is of course new data from LHC coming in since 2017 that we can use and we are using in order to improve our fit. But there has also been in the last year, there has been finally a publication by the sequest experiment. So sequest is one of this is the current fixed target experiment at Fermilab, where they take a proton beam and then they hit it on a fixed target, which is typically something like deuterium or another solid target. And this has been designed as a follow-up of previous fixed target experiments, which they had when they were probing the Drell-Yan cross-section. And this was specifically designed to measure and explore the U and D C quark PDFs at high X. So in connection with new physics searches, we were particularly interested in seeing and understanding what kind of constraints we are getting. You should understand these fixed target experiments, they operate at fairly low scale. So here we are talking invariant masses of the final state of the order of 5 GeV. So if you go back to the parton kinematics plane that we are having here, so we are really sitting down here, and then we have to evolve with perturbative evolution. We have to evolve the information all the way up here. But I think we know how to do this, and this can be controlled. So this is sequest. And the parton kinematics plane of sequest compared to all the other data that we have been using so far is plotted here in this plot. So since sequest is a fixed target experiment, the kinematics is asymmetric. You have one x, which is sitting at high x, and the other one is sitting at a little bit smaller x values. And then you see up here the red dots. This is basically sequest data. So the 1x goes up to 0.7, 0.8 here. And the other x is sitting here a little bit smaller at around 0.4. And this can be contrasted here with E866 and E605. So this has been these have been the previous fixed target experiments. And you see that sequest really extends a little bit here. But if you compare this to what is already known now from the LHC on the parton kinematics for the Drell-Yan process, then we have here, down here, we have data from LHCb. And you see, due to the asymmetric configuration of LHCb, you also go down, you go down to very small x values, but you also have a reach up to very high x values. So we are basically probing already at the LHC those high x values that are now also being covered by sequest. And here in between, those blue dots, they are from tevatron charged lepton asymmetry, and they have a similar reach here. So we actually have good knowledge on this parton kinematics, and we just try to understand now whether all of these data is compatible with each other. And to that end, we did a variant of this ABMP16 fit, just running the nominal fit and then also adding sequest data and looking specifically on the constraints of the light flavor PDFs. So here on the left-hand side, you see the D bar minus U bar, so the isospin asymmetry that we are getting here at large values of x. So this is at the low scale where you would start the evolution. And you see the blue band is what we had previously from ABMP. And now with the sequest data, the uncertainty band becomes a little bit smaller. So we are actually learning something more, and we get slightly better constraints. And on the right-hand side, you have the ratio of the D bar over the U bar, also as we go to large X. So eventually, this should vanish if we go with X to 1. But you see this has a large uncertainty here, but the trend is quite clear and everything is compatible. Yeah? So that's good news. That's good news. And then we could also look at how other PDF sets are predicting, especially this D bar over U bar ratio. And this we have in this plot here. This is now at a higher scale of 25.5 GeV squared. This is where CTEC themselves extracted this D bar over U bar ratio. So there you see these black dots, which are the CTEC data, sequest data that you see here. And then the blue and the red dashed bands, this is from the ABMP16 and the variant of the fits. So that is what you see here. And then the green band, this is the uncertainty that you get from NNPDF 4.0. And this is remarkable. First of all, because you see the uncertainty is really very large, just already in a range which is still covered by data. But it is also, the NNPDF fit also doesn't really seem to be efficient, because you see the uncertainties which they quote here, they are still larger than the experimental uncertainty, despite the fact that this data has actually been included in the NNPDF fit. Yeah? So they've included this data in the fit, they have fitted everything, and still the fit hasn't been efficient in order for them to come up with reduced uncertainties here. Yeah? So this is remarkable, and we'll come back to this later. Now we also looked then at cross-section ratio. So since this sequest is a deuterium target, we've been looking at the predictions at the cross-section ratio, taking the cross-section for proton on deuterium, dividing it by proton-proton, and then looking at the pulse by just subtracting the theory. So basically, if everything is compatible, we should be here at 0. And then these are the poles of the deviation and also give you an idea on the accuracy of this data. So you see you're having here, by and large, uncertainties of plus or minus 5 to 10% basically here. Yeah. But here you see that we are largely compatible as far as ABM-P fits are concerned with the data. There is this high X point, which is off by maybe a little bit more than 1 sigma. NNPDF comes with much larger uncertainties here, and they seem to cover everything. Other PDF sets like for instance, the CJ15, which has been an earlier fit by the Jefferson branch of CTEC, they are slightly off here. And then also what is particularly off is the early Atlas fit, when they were in 2016 for the first time doing their own PDF fits. And they had then employed a model which was based on an SU3 symmetric Walksy model. And you see this doesn't really describe any of those data. They have corrected it since then. So follow-up fits of Atlas have improved upon this. So this is kind of a legacy comparison which we have here. Good. One word on the deuterium target. So basically deuterium is, of course, it's not just having a free proton and a free neutron, but you also have bound state corrections. And there are actually models for calculating these nuclear modifications. And we have calculated them and determined them. And these are the ratios for the individual PDFs. This is based on a model by Sergei Kulagin and Roberto Petti, where we basically take the valence, the U valence in the deuterium divided by the free U valence in the proton and the neutron. And then if there are no nuclear corrections, everything should be 1. And you see there is a small trend here. So of the order of plus 1.5%, but they're typically small. And if you look at the uncertainties of the data, for that case, we don't really have to worry too much about nuclear corrections here. So this is as a function of the Feynman variable XF here. This is also because this is kinematics that has been used in the analysis of the sequest experiment. So this is just to say we have nuclear corrections under control. And then finally, what does it tell us about new physics searches? As I said, we want to explore the TeV region. This is what squeezes us to look at parton kinematics at high X. So we can basically do direct searches. We can look for possible signatures of C prime gauge bosons at these high scales, or we can set up a formalism where we take the Smith-Lagrangian at dimension 6 operators with 3 couplings and then see if in such data there are possible deviations for the values of those couplings from the standard model. Since I told you we have parton kinematics covered up to high X, but yet if you go really to the edge of the available phase space at the LHC, at some point you are leaving what has been measured so far, and also you don't want to use those data in order to constrain PDFs and fit away any signs of new physics. So you have to ask yourself, what is a way to try to assess in a meaningful or systematic way any PDF uncertainties at large X? Because if you, as you've seen with the NNPDF example, if you just take those results at face value, then they dominate the whole error budget and you cannot meaningfully say anything. Yeah. So you need to estimate the PDF uncertainties beyond the measured kinematic range. And this is something we did in collaboration with this BSM people, so Stefano Moretti and collaborators. So we basically said, okay, large X PDFs are basically dominated by this 1 minus x to the power b part in this parameterization. And I have shown you before the numbers and the accuracy to which we can determine those coefficients, just fitting the data. But say we just vary them by a reasonable amount, say 0.3 or 0.5, just to see how much are cross-sections changing when we're doing this. And this is what we did here. what we did here in this plot, where we plot the Z boson production for high invariant masses, going from the peak here, which you see at the left-hand side, then all the way up to 8 TeV in the invariant mass. And then this is the prediction here with taking ABMP16 and then allow PDFs, but then using this additional variation on the large X exponent here. And then on the right-hand side, we've also compared it to other predictions from other PDF sets. Most of them, like MSHT and CTEC, they are compatible. And then what sticks really out here is NNPDF in the high TeV range. So this is certainly off. And also here, the quoted uncertainty is then to be discussed, or is questionable. Yeah. Right. So this is then for high invariant masses, and just to tell you how could new physics pop up there. So if you just put in some Z prime boson, and you have two parameters, you can take the mass of the Z prime boson and you can take its decay width. So if you take a heavy Z prime boson of 6 TeV and you make it narrow in the decay width, so gamma over m take 1%, then you would be having bumps like this here for various models. So all these colored curves here are various models where the Z prime boson could pop up, motivated by extensions of the standard model gauge group. And if you make the Z prime boson a bit lighter, like 4 TeV, but then make it very broad, then you see basically in the tail of the invariant mass distribution, you start to see some plateau here, and then it levels off. And certainly a broad heavy particle is something you would not want to miss under some parton luminosity uncertainties here. Now this is for the differential distribution. Then the BSM people went forward and looked at quantities which are even better suited to do such new physics searches. And one thing which is discussed and put forward here as an observable is the forward-backward asymmetry, AFB. We basically take the difference between the leptons left and the leptons right and normalize it by the total cross-section. And then on the left-hand side, we have here the AFB asymmetry in the invariant mass, again going up to 10 TeV roughly. And this is here with the prediction which we have computed based on ABMP16 with this variation of the large X exponent. And on the right-hand side, we have again compared the forward-backward asymmetry with other PDF predictions like CTEC, MSHT, and then also NNPDF. And most of them are consistent. The only thing that really sticks out is the NNPDF result here, which starts off with a positive forward-backward asymmetry, and then suddenly at 4 TeV, it's almost like a phase transition, and then you have a negative forward-backward asymmetry. So that's certainly remarkable, and we'd like to understand this a bit better. And I'll explain you what's the reason for that. Just to say, if we take the same new physics models for a Z prime, for heavy Z primes, on the one hand, the heavy Z prime 6 TeV with a narrow decay width, then it would pop up in a significant way in the asymmetry here. If we take a little bit lighter one, which is broader, it would also leave a clear trace in the forward-backward asymmetry. So this is actually good observable to look for deviations of the standard model. But of course, you have to control the input parameters, especially the PDFs. And so if you go back and you think of the NNPDF result here, then the question is, if you take this, then how do you distinguish it from new physics here? So this is what then also led us to try to understand a little bit better the prediction by NNPDF. And to that end, I should just point out to you, just recall the Z boson cross-section at leading order, how it depends on the parton kinematic. So it's just the sum of U bar times DD bar. So this is the cross-section. Now, if you split this into forward and backward, you're basically taking 2 times the thing and you take the difference of the 2 quantities, but then the PDFs evaluated at different X values. And you can then look at the slope of the light flavor PDFs as a function as you approach the large X limit. So you basically take the log derivative of your PDFs. You take the derivative with respect to log 1 minus X. This is basically getting you this exponent or the profile of this function as you approach the limit. And then in order to get a positive forward-backward asymmetry across all ranges of the invariant mass of your dilepton final state, you have a constraint on these slopes of the light flavor PDFs. Namely, the slope of the light flavor C distributions for the U and the D has to be always larger than the slope of the valence U and the valence D. So the UC has to have a steeper slope than the U valence, and the DC has to have a steeper slope than the D valence for all values of X. So that cannot change anywhere in between. That has to hold. And I just wanted to remind you, if you go back to the numbers that we had here for ABMP16, so we have a large X coefficient for the U quark, which is 3.5. For the UC, we have 7. So this is fulfilled, for example, for the U valence, we have 4.4, and for the DC, we have 8.4. So this is also fulfilled. So for us, we are therefore getting a positive forward-backward asymmetry. And now if you look at this slope for NNPDF, this is a plot which they had provided by themselves some time ago. Then you see this is the slope for the U valence. This is kind of positive, but then for the UC, they suddenly, as they go to larger X values, the UC distribution decreases its approach to X. It even changes sign here. It becomes a bit, it decreases, and then it stops, and then it even grows a little bit again. And so this feature here is basically responsible then for a forward-backward asymmetry that is changing sign somewhere then in the middle of its invariant mass spectrum. And then the uncertainty band, which NNPDF quotes together with what I've shown you with the efficiency of the fit to the sequence data, leads us to the conclusion that there is not really any predictive power in the NNPDF set as you go for for new physics searches in the high X tail of the parton kinematics. Yeah? So we would really argue that based on all the data we have, and also based on prejudice which we have about the simple functional form of PDFs as you go to a kinematic limit, we should have this hierarchy. So the large X exponent of the valence should be smaller than the large X exponent of the C, and that should hold for all values of X. And therefore, we would argue you should come up with a positive forward-backward asymmetry as you do the searches at the LHC. Right. So that's the story here. As an outlook, of course, we would like to advise experimentalists that they should not rely on us theorists giving them one or the other input. They should make up their mind about what they are using. So we would like, we're in discussion to develop data-driven approaches so that they could, for example, form ratios of cross-sections where they use parton kinematics from a control region and then do their own assumptions on how to extrapolate this. But if they work with ratios, then they can already cancel a lot of things there. This is certainly something to be developed further for Z prime boson searches. Then if you want to go to SMEFT, to a full SMEFT study, Sasha Tsenaev has already told us how this can be implemented in XFitter framework. So this is also work in progress. And these are basically the tools that experimentalists then should use. So they should use certain selected data sets and then do their own fits, for example, in XFitter. From a theory side, what we can still add to this discussion, we can add that we also, of course, have access to other sources for determining PDFs. And here in particular, we have data from Lattice QCD. So the Lattice people are able to measure certain moments of light flavor PDFs on a lattice. So they just put some quark operators there, and then they compute preferably the second moment of the unpolarized PDFs. So what they can measure best is actually the isospin asymmetry, so difference between U and D. This is what they can measure best now, also at physical pion masses. So for a long time, this has also been a struggle for them to go down, to go with lattice sizes to a point that they can really simulate physical pion masses. But from a number of collaborations, we now have lattice data for the second moment, and this can be compared with determinations from various global PDF fits. Since the numbers are a bit hard to read, I've put them here in a file. So this dashed band here is the result for the U minus D from ABMP 16 at NNLO with uncertainties. And then here you see you have the various results from lattice. What is noticeable is that lattice errors are still significantly larger than what you get from experimental determinations. I try to motivate lattice friends to redo these computations. They tell me it's hard, but it's certainly space to watch, so that maybe one day we can also have a precise lattice number here, which then could discriminate at least between some of these values that we get from a fit. Okay, that brings me to the summary. So I focus specifically on parton distributions at Ti-X. I tried to convince you that we already have very good understanding based on data from the Large Hadron Collider, supplemented by other fixed target experiments, and that we really have a good understanding also on the light flavor separation, much better than, for example, 10 years ago. And that you can use this in order to also conduct meaningful new physics searches in that range, and that we should come up as a community also with good prescriptions for the experimentalists, so that they can then do their own implement their own assumptions on how to extrapolate PDFs to the search window where they are looking for effects. That's it. Thank you very much.
Yes. Let me start.
So, I mean, I fully understand the logic of trying to get better PDF to predict new physics. Okay, this is absolutely crucial. However, I mean, I have a concern because, so here you are starting from your fit of 2016, which is not a global fit. No, you have a restricted amount of data that you put there. And you are adding these forward results. So, and then you are telling me that you have some tension with NMPDF, but are you able to describe the LXC data, for example? So how does your fit perform with the other data that are included in NMPDF? And for example, what is the issue with alpha S? Because typically in your fits, you have very low alpha S. So this was always an issue. So I'm wondering if to sort of go in the right direction in the forward region, you are screwing up somewhere else. Okay, that's very naively my concern.
Yeah, okay, so thanks for the comment. So basically, in adding the sequence data, this is what we started with. we have all the previous Z boson data from D0 and from LHC. We have it still in. We get a good description. We've been checking since then on the new data. We also get reasonably good description on the new Drell-Yan data at 13 TeV. So that is fine. For the light flavor PDFs, the issue of alpha S has a lesser impact than when we're talking, for example, TD bar cross section or jets. Yeah, so this has a lesser effect there. So it is really the Drell-Yan data telling you how to do this flavor separation. This is where it has a main impact, and there we're getting good descriptions on all other data sets. So this is why we would say we're having a valid description here, and on that basis we can then ask ourselves, how would we go beyond the measured kinematic range? And this variation of the large X exponent by some amount was, you can argue it's ad hoc. It is one prescription, but I'm totally open to any other advice or suggestion there. Yeah.
Do you like to comment on alpha S, even though it has a lesser impact?
Well, alpha S is the nominal value which we get here is from NetFit is 0.1147 for 5 flavors with an uncertainty of roughly 0.01, and this is about 2 to 3 sigma tension if you would consider alpha S whatever world average of 0.118, for example. Yeah, but as I said, the alpha S for that particular issue, alpha S doesn't have a large pull here, so there is not really we don't shift alpha S by a large amount for that given. Sorry? It is more connected to the gluon. So if we were discussing for Higgs boson cross-section gluon fusion now, then of course alpha S would be a big issue which we should discuss. Yeah.
Thank you, Sven.
So a few years ago, there has been a proposal by the CETA collaboration to use Drell-Yan data at intermediate or like rather large center of mass energies, but say a TeV or so, to constrain the PDFs directly, and then probe the multi-TeV range. So in order to have less extrapolation. I see this in the context of your remark where you say the experimental colleagues should be enabled to provide different schemes to do the extrapolation. Would theory input or like fits along these lines by theorists, would that be something good to do in your mind? Would you like to comment on that, please?
We've been discussing this already with Sasha Tsenaev and XFitter. The point is, of course, you can take a given PDF set and then you can start with such tools to do reweighting of the different PDF sets, but then you're still bound to some theory assumptions which went in there. So I think the better approach for experimentalists is actually to use such a fitting framework and then to use data from a control region, say up to 1 TeV, do whatever uncertainty estimates they want to do there, and then propagate this by themselves. So I would really advocate more like a data-driven approach, but maybe Sasha can add to this as well. Yeah, okay.
Okay, yes, Sandro.
I would like to understand if you can elaborate more on the constraint for the slope between C and valence. And I'm asking this to understand what happens then in the forward-backward asymmetry, because the forward-backward asymmetry is essentially possible only because you have an imbalance between C, between valence and C, which you get at large rapidities. Now, with your constraint, I guess you can get it. I was wondering how solid is this constraint?
Of course, this is based on analysis of leading order kinematics, but given the smallness of higher order corrections, it is called. I think it carries a long way. So it's actually quite helpful to understand this, and then you should, if you work out what how these, I don't have the formula in here, but the NNPDF people, they worked it out in their paper. when they made these plots. If you work out how you can express the forward-backward asymmetry, especially its change in terms of these slope parameters, then you realize in the end that you basically have to have this positivity constraint. Otherwise, at some point, AFB switches sign. So this is what you can work out. And it has been spelled out here in this reference. So they realized it by themselves. And on the solidity of this argument, I would just say, I've given you the numbers and the accuracy to which we can fit this large X exponent here. So we're talking basically fractional units here. So this is why we also suggested variations of, say, 0.5 in our approach, which would basically move this up and down a little bit. But what is certainly not really physically intuitive is that you suddenly have variations in this large X exponent, which are of the order of 100% basically. Yeah, so you go down from 10 to whatever to 0 here. This is not really, it doesn't match any physics model I would have in the back of my mind for the valence die. The C dies are faster than the valence. I mean, the C is basically driven by the gluon, so it doesn't have any, so you just build up C by the gluon. So this is why it's really suppressed at large X. You just pull it out of the gluon, and the valence dies off with a certain X power, but it dies off slower than, for example, the gluon. So gluon and C quarks, they die off fast as you go to large X. Valence is the last ones. And then you have, right. But then when this holds for all values of X, then you have a positive asymmetry. And the case for NNPDF is that for the U valence here, and D is the same, for the U valence, you always have a slope around 4 here. And suddenly for the C, you drop to a slope of 2.5 or so. And this is precisely what translates then into the sign changing asymmetry at 4 TeV. Yeah. If they had a slope change only at 0.6 or even higher, then this would shift accordingly. So this fall off here is precisely what is switching the sign in the forward-backward asymmetry. And then I think it depends. It's up to everyone to basically confront this to his or her own physical prejudice to see if this is reasonable or not. Yeah?
Emanuele, do you want to say? I don't know if anybody is still there.
Very, very naive observation. Does this trend show up also for older and NPDF sets? The reason I'm asking is that my understanding is that, I mean, when you change from 3 to 4, there are significant changes in the whole machinery.
I don't know this by heart. What I just can tell you out of my memory is that the tails of the distribution, be it small or large X, have always been difficult with NNPDF. I mean, they always came up with uncertainties which somehow seem to be less under control compared to other parameterizations. So therefore, I haven't checked this particular thing with older NNPDF versions, but certainly the large X uncertainty for NNPDF on this D bar over U bar, this has always been very large and much larger than anyone else. Yeah.
Since you're focusing on large X, shouldn't one worry about resummation in the coefficient functions?
That's a good issue. I mean, this has been there has been, I think, one fit by NNPDF. From our side, we never got a gist on its effect compared to other theory differences that we are seeing when we compare to other global fits. Yeah. So one thing we discussed is efficiency of the fit. Other things is then if you go to other data sets and you look at theory input for DIS, for example. So there are a lot of other differences which to our understanding cause much larger deviations. So this is why we didn't focus so far on this resumation. I think at some point when you really have very good understanding of that part, a dedicated study would certainly be worthwhile doing. Yeah.
Thank you.
I endorse the point by Simone that this X is so large that sizable effect. I mean, we had some ancient small studies way back then with Gennaro Corcella. Things do move once you get out to like 0.5, 0.6, 0.7.
Yeah.
Any other question? No. So let's thank Sven again. Thank you very much.